We have a talk. Thanks. Our next speaker will be Aurèle, who is talking about just-in-time compilation in CompCert. Thanks.
Thank you. So, yes, our work is about the formal verification of just-in-time compilation. And more precisely, it's about the formal verification of native code generation and execution in a just-in-time or JIT compiler. So generally, just-in-time compilation is a technique to execute a program where we interleave execution and optimization of the program. Just-in-time compilers are particularly popular for executing dynamic languages, which explains that most modern web browsers today use JIT compilers to execute JavaScript programs. But that's not all. There are actually many other use cases of JIT compilers, and you can think about eBPF, Python, Java, and many others. The takeaway here is that billions of people use JITs every day, and so we want to avoid bugs in JITs. To avoid bugs in compilation, we know from traditional or static compilation that we can use formal verification and we can try and formally verify our compilers. In the case of static compilation, this has given many great works about formally verified static compilers, such as CompCert, KKML, or Vellum, which are all compilers that not only transform a program into a corresponding native program, but they also come with a formal proof of correctness, meaning that, for instance, we can formally prove that every observable behavior of your native program on the right is also a behavior of your source program semantics. And if you prove this formally, you have proved that your compiler did not introduce any bugs in the program you are compiling. So, of course, this raises the question, what about formally verified just-in-time compilation? Can we design formally verified JIT compilers? And the execution of a JIT compiler is going to be quite different than the execution of a statically compiled program. And so our proof techniques are going to be different as well. Let's look at a simple example of executing a program with a JIT. Let's say that I want to execute my program on the right. So I have a simple function f that is repeatedly calling another function g. So as I said, JIT compilers are going to interleave execution and optimization of the program. So one way to begin with the execution is to call an interpreter, for instance, for function f. So in my execution stack, I can see a stack frame for the interpreter executing function f. I will make some progress in f, and after a while, I will see a call to g, and so I can call once again my interpreter to execute function g. I will do this for a while, return to f, and then execute g again. And after a while, maybe the JIT compiler will notice that function g is being called a lot, and so it would be worthwhile to start and optimize it. So dynamically, JIT compilers are going to call an optimizing compiler to produce a new version of function g so that its next calls are faster. So for instance, here we can insert a new version of g, for instance in x86, and this version should be faster to execute. In modern JITs, we can even use speculation, meaning that we can try and speculate on the future behavior of the program. So for instance, we can say that we believe that variable x is going to be a 32-bit integers, and so we insert the speculation, and if we are correct, the remaining of the code will be specialized to that behavior and even faster. So next time we want to call g, we can call this new version of g, and so it should be fast. And we're going to check that speculation at runtime, and most of the time it's going to be true, but sometimes it may be wrong as well. And in that case, when the speculation fails, we want to return to the original version of g that is correct for any context. And so this is what we call the optimization, and this requires a particular case of on-stack replacement, meaning that I'm going to discard the native stack frame and try and synthesize a stack frame for the interpreter executing the original version of g. The takeaway from this complex execution is that in a JIT, multiple languages can happen to be executed and synchronized. And also because we have speculation and the optimization, JITs need this unusual and quite precise manipulation of the execution stack. So our goal is to design formally verified JITs that come with a proof of correctness. And previously, 2 years ago, we had some previous work about a formally verified JIT. So this JIT was focusing on dynamic and speculative optimizations, meaning that we designed an intermediate language, an intermediate representation for speculative instructions and speculation in a JIT. And on this language, we proved the correctness of some code transformations that insert and manipulate speculation. However, there was still a missing feature in that prototype. In the formal model, there was no native code generation, meaning that our correctness theorem was only about interpretation and optimization at the same IR level. So now we want to bridge that gap because generating native code is a specific feature of JITs. And so we want to prove the correctness of a JIT compiler with native code generation and execution. Now, of course, this brings new verification challenges. The first one is that because we have native code execution, some of the components of the JIT are going to be hard to write in Galena, the programming language of CompCe. So to solve this issue, we're going to adapt a free monadic encoding of the JIT. And in that encoding, some small set of primitives are going to be given a simple and CompCe specification. Another issue is that we would like to reuse everything that we know about formally verified static compilation to generate native code. And so we have been able to integrate the CompCert backend to generate native code in a JIT, and also the proof of the backend to formally verify this generation. We have also defined semantics for interleaving the native code that is being dynamically generated with the rest of the other JIT components. So what does it mean exactly to prove a JIT correct? Because we know how to prove static compilers correct, and we can actually make something really similar. So for instance, here is one of the correctness theorems that you can find in CompCert, and we can try and read it line by line. It says that if you compile a source program P, and it gives you another compiled program TP, and if P has no wrong behaviors, meaning that it does not crash, for instance, then every behavior of your compiled program TP is also a behavior of your source program P according to its semantics. So if you prove this, you know that your compiler did not introduce any bugs. Well, for a JIT, we can have something really similar. We can have this following theorem that says that for every program P that we want to execute with our JIT, if P has no wrong behaviors, then every behavior of the JIT executing P is also a behavior of P according to its semantics. So now the difference is we are no longer mentioning the static compilation inside the theorem, because compilation itself is going to happen into the JIT semantics because it's going to happen during execution. So now to define the JIT in such a way that we can have such a JIT semantics to reason about, what we can do is define the JIT as a state machine alternating between all of its components. So speaking of components, our first component on top is going to be called the monitor, and it's a component that's just going to decide which component to call. Are we going to optimize next, or are we going to call the interpreter, or every other component? Next, we also have an interpreter if we want to execute the code that has not been compiled yet. For the optimization, we do it in several steps. And our first step, we call the middle end. And basically, it's responsible for inserting and manipulating speculation into our programs. And if we focus on just those three first components, it's what our previous work was reasoning about. But now we want to also integrate backend and native code generation. So of course, our next step is backend compilation. So here we can reuse the CompCert backend to generate some x86 code from RTL, Register Transfer Language, one of the languages of CompCert. Finally, when we have generated some native code, we want to install it in the memory and make it executable so that we can next call it. On the right, there is two other components. If we want to execute native code that has been dynamically compiled, we can load the function that we just generated and then run the generated code. Now, most of the boxes here can be defined in CompCe as a simple and pure and terminating Galena function, but some of them are going to be hard because we have native code generation. So some components are impure because, for instance, we have some data structures that are shared and accessed by both the native code but also the other JIT components written in Galena. Moreover, when we compile a function, we may have compiled a non-terminating function, so we may also have non-terminating behaviors. So we are faced with the challenge of trying to verify in Coq a program that we don't really know how to write in Coq. Fortunately, we are not the first ones with this issue. And for instance, both interaction trees and FreeSpec have been using a variation of the free monad to represent and reason about impure programs in Coq. And so we're going to do something a bit similar. So let's talk a bit more about this monadic encoding. Basically, the main idea is that most parts of the JIT can be written as pure Coq functions, but some of them cannot really. So we're going to use the free monadic encoding to write incomplete programs, and we're going to write exactly what we can write in Coq and leave the rest unimplemented. So for instance, on top of the diagram, you can see that the JIT is written as an incomplete program in the free monad. And so then we can complete those incomplete programs in two different ways. On the left, we can give some monadic specifications to the primitives that the JIT is using, and this will help us define the JIT semantics that you could see in the theorem, and so we can reason about that. On the right, however, we can extract this free monadic computation to an OCaml equivalent program and complete it with impure implementations of the primitive in OCaml or in C, for instance, and this gives us an executable JIT. And if you trust that the specifications of the primitive corresponds to their implementations, then your correctness proof should also hold for the executable JIT. So let's try to go a bit into details. I'm going to show an example where we only have two very simple primitives. Let's say that we want to access a single global variable of type nat. So I just want two primitives, get and put, that I list here in this example. So get returns something of type nat, and put takes an argument and returns something of the type unit. I can actually define my free monadic encoding with this simple definition. I'm going to say that a free monadic computation of type t, returning something of type t, is either a pure computation with no primitives, so just a Galena term, basically, or an impure computation consisting in first calling a primitive that returns something of type R, and then a continuation next that tells me what to do with the result of that primitive. And this turns out to be a monad, so we have some monadic constructors to build complex computations. So this is how we're going to bind three monadic computations together. If I want to do F and then G, if F is pure, I can just give the value to G, and if F is impure, I can recursively bind the continuation of F with G. So this is a really simple way to encode incomplete programs because I did not give any implementations for get and put. And now we're going to see how we can complete it. So as I've said, the first way to complete that is to try and write a Coq specification for each of the primitive. So to do this, I'm going to use a standard state monadic encoding because I'm accessing a global state. So for instance, for get, I can use a function that returns to me what's in the state, and for put, I can write this state monadic function that's going to modify what's in the state. Now that I have these specifications, I can finally give semantics to my free monadic computations by simply replacing each primitive with its state monadic specification. So if my function was pure, I'm just going to return that term, and if there is a primitive, I'm going to bind the specification to the semantics of the continuation. So this is how we get our semantics, but we also want to get an actual executable implementation. And so we can extract our free monadic computations to similar ones in OCaml and then complete it with actual impure implementation. So still in my same example, what I can do now that I'm in OCaml is use a global reference, for instance. So for get, I'm going to use this reference, and for put, I'm going to update this reference. And finally, I can write this simple function that's going to execute my free monadic computations by taking the corresponding implementation of the primitives. So this is all we need to write our incomplete JIT. So every component can be written in this way. So if I go back to the optimizer of my JIT, I can write it this way. I can first use a function to generate some RTL code from my IR function. So this, you see a right keyword, meaning that this is a purely pure computation. Next, I can use a CompCert backend to generate some native code. And finally, I can try and install that code by using a primitive. Of course, when I give implementation to that primitive, I'm going to need to write some C code in my case. So for this primitive that installs code, we can write a primitive that calls an assembler to produce binary code that allocates some memory, writes into it, and makes it executable. So now that we can represent our JIT, we also needed to prove the correctness of it, and in particular of the backend compiler. And basically, we are reusing CompCert. So we know that CompCert preserves the observable behavior of the program. So in that diagram, we know that the red arrow is somehow equivalent to the blue arrow. So if I try to use it in a JIT to compile a single function, I should also have preserved the same observable behavior of the program. However, if I want to reuse CompCert as is, and also have the two bottom orange arrows to be equivalent, I actually need to preserve a little bit more than the observable behaviors. I also want those two arrows to have the same effects on the stack and the heap. And so our solution was to make the generated native code interact with the stack and the heap, using only our primitive, external calls to our primitives of the free monadic encoding. Another issue is that in a JIT, we want to regularly come back to the monitor to decide when to optimize. And so our solution here was to design and use custom calling conventions in the generated native code to go back to the monitor. So in this simple example, let's see on the right that I have a function that contains some instruction and then a call to another function. What we are actually doing is generating several RTL programs. So we first generate the first one that contains the first instruction, and then contains some calls to our primitives to save the environment to the execution stack of the JIT. Next, we can return to the monitor that may optimize the function, execute it, and when it's done, it will go back to that second continuation program that restores the environment using, once again, our primitives. So yeah, we do not let CompCert manage the JIT heap and the stack. We do it only using our small set of primitives. So about the proof, we are doing it in two steps for the backend. We first have a first step that generates several RTL programs with our custom calling conventions. And this we can prove with a forward simulation that is in general much easier than a backward one. Next, we can use a theorem from CompCert to generate a backward simulation for that same path. And so we get this kind of backward simulation that gets us the preservation of observable behaviors. For the second pass, however, we are using the CompCert backend, so we know that there is a backward simulation for each of the programs that we compiled. And so our task was to prove that if we have a backward simulations for each of these programs, we also have a backward simulation for the entire programs that contains interpreted code and also native code. In the end, we get a simple specification of our optimization. If we have optimized a program, then we get a backward simulation, and this is what we want to get behavior preservation. Here is a simple list of primitives that our JIT uses. So we have a first few primitives to handle the stack and the heap of the JIT. So for instance, we can pop and push some integers to the stack. We can also do the same in the heap of the JIT. And those first few primitives can also be called from the native code when we implement our custom calling conventions. Finally, we have some other primitives to install some native code into the memory and run some native code. And running native code is a bit special because it can be non-terminating, but I don't really have time right now. In conclusion, we have added some things in our trusted code base because now for each of the primitive, we have to trust the state monadic specifications of them. But now we finally have a formally verified JIT that contains native code generation and execution in its formal model and in its correctness proof. We have been able to reuse much from CompCert, including the simulation framework, the backend to generate native code, and also the proof of the backend. And we also get an executable impure OCaml JIT that you can actually use to run some example programs. Thank you.
Thank you for a great talk. I'm Jiyoung Kang, KAIST Korea. And you said that you implemented the JIT compiler, and how fast is it, basically?
So performance was not really our concern. First, we wanted to have a formally verified implementation with all of the characteristic features of JIT. So we have really compared it to like using interpretation alone. And so without surprise, it's much faster than using interpretation alone. The numbers themselves are not really representatives because we targeted some very simple programs, but we can get like 40 times faster than interpretation. But also our interpreter is not really meant to be efficient. So yes, there are some things that could be a bottleneck for execution, like when calling our primitives, but we also believe that this could be later refined into a more efficient implementation.
Thank you.
Yeah.
Thank you. Great talk. Zhong Shao from Yale University. So when you talk about the TCB, do you also include the assembler, x86 assembly to the binary code?
Yes, definitely. This is a very simplified version. In the paper, it's a bit more elaborate, but we also stop at the assembly level, just like CompCert. So of course, we need to trust the assembly to produce the correct binary code.
So it falls into one of these primitives, or it's just something else?
It falls into one of the primitives, the one that installs the code into the memory.
Hi, I'm Young Song, and thank you for the great talk. I have two questions. So, at least some motivation for using the free monad sounded like defining the non-terminating term inside code, and doesn't that imply that you need to use co-inductive data type? And the second question is that, can you compare your free monad against interaction tree in a little bit more detail?
Yes, that's a very good question. I think I can answer both at the same time. So yeah, interaction trees are a co-inductive variant. But we have found that in our specific case, we didn't really need it to have this co-inductive, because when I say that I have a special primitive to run the native code, I'm actually dividing this into small steps that corresponds to the x86 semantics. So each of these steps actually terminate, and so I can reason about the small step semantics of the entire JIT execution using this sort of decomposition. This also gets much smaller meta theory needed to reason about everything.
Thank you.
Final quick question, Adam?
Near the beginning, you mentioned how JIT compilation is usually used with dynamic languages, where, for instance, we optimize based on a hypothesis about dynamic type information. So do I understand right, you have an interpreter for a CompCert intermediate language? And I'm also wondering what kind of information you learn at runtime that drives optimizations that wouldn't be routine to do with ahead of time compilation.
So this I did not talk much about today, because this was more about our previous paper. So yes, it's a CompCert intermediate language, but also extended with some instructions for speculations. And those instructions are actually quite close than what is used in the RJIT developed by Jan Vitek, Olivier Flukiger, and others. And so for the information that we gather ourselves, it's really simple, but we have also proved that whatever information we want to gather, whatever profiling heuristics we use, the correctness proof is still correct. So I haven't focused too much on realistic profiling heuristics, but it would be interesting as well.
Thank you.
Thanks again, Aurèle.